Hi, Miss Byrne here. This is a video focusing on torque, part 2 of our unit on rotation. So the concept of arm wrestling and many sports have to do with torque. So to be successful here, you have to exert a force on the other person's hand, perpendicular to the arm. And that's what we're really thinking about here when we're thinking about torque. Which of these forces would be more effective to open a door? Force 4 here, close to the hinge or the pivot of our system, isn't really how we open doors. Often it's pretty hard to push a door right here. Most effective would be to push at the furthest point of the door and in a direction perpendicular to what's called the lever arm or the moment arm or the radial line. So perpendicular to this direction from the radius out to the point of the force acting. So pushing along the edge of the door, not going to open the door, and if you push at some angle, it will be more challenging to open the door as well. So this is our idea of torque, that if we increase the distance from the pivot point that we exert a force, we can exert a greater torque, and if we increase the force, we can exert a greater torque. It needs to be perpendicular, the force, in order to be the greatest torque. We should exert the force perpendicular to the radial line. So let me just start this again. So as the force goes from perpendicular to parallel to the radial line, the part of the force that acts perpendicular gets smaller and smaller, and that would cause less and less torque. So the angle of the force is important. So what is torque? So torque is essentially the angular analog of force. It causes an object to rotate about its axis, about its pivot point, its rotation axis. In your reference table, it's expressed as, I think it's actually R perpendicular F, but I'll write F perpendicular R, and that's equal to FR sine theta. And what this sine theta is really doing is kind of forcing you to look at the perpendicular component of the force. So R is the distance from the pivot that the force is applied, or also called the moment arm or the lever arm, and it's a vector, and only the component of the force perpendicular to the moment arm causes a torque. So if we deconstruct our force here at an angle, we can see that the perpendicular component, if we have our angle measured with respect to the radial line, can be calculated as F sine theta. So this angle is measured from the radial line. Or measured from that extension of the moment arm. So really, I don't often use FR sine theta because I just check myself, okay, is this the perpendicular component of that force? Because sometimes sine theta isn't going to work out if they don't give us the angle that's measured, from this radial line upward. So what direction does torque twist something? So we're going to define as our convention that a positive would be counterclockwise, or CW, and negative is clockwise, CW. So do these forces do any torque? And if they do, what direction would it be? So this force, because it's parallel with the radial line, does no torque. So go ahead and think about that, pause the video, and I have P on the next slide. So this one would do positive torque because if this was exerted, it would rotate it in the counterclockwise direction. This one would do negative torque, and then it would rotate it in the clockwise direction. And then as they go further from the perpendicular, they exert less torque. So let's look at another example question. Here's another example. When a wheel turns freely on its axle at the center, given the information shown, which of the forces provides the largest positive torque? So let's go through each one. So A torque, again, is force times the radius. In this case, the radius is r. But A is going to turn it clockwise, so it's going to be negative 2f times the radius r. B is going to turn it in that same direction, the negative direction, 2f times the radius r over 2. C is going to do no torque because it's exerted right at that axle. D, again, is going to do no torque because it's not perpendicular to the radial line. So E, hopefully, exerts some positive torque, totally does. So it twists it or rotates this object in the counterclockwise direction, so it would be positive F. So we can calculate torque with the F times R, and we can calculate the sum of the torques by adding up all of the F's times R's. So if we look at equilibrium scenarios, in this case, the net torque is 0. It's balanced. So the big idea around torque in general is it's angular force. So a net torque causes angular acceleration, just like a net force causes linear acceleration. So when we're in equilibrium, we have an angular acceleration, that's the fish, or alpha of 0, so the net torque is 0. So if we look at the torque from two objects, or two forces, F1 at a position R1 from the pivot point, plus, and then we would call the other one negative because it would exert it in the other direction if we had these two people on either side of the pivot. So plus the force the other one exerts times its distance from the pivot, we would set that equal to 0. And so those two torques are equal to each other. They're in equilibrium. So let's do an example problem. How far away from the pivot should I put a 100 Newton force to balance it? So we have a person standing on the other side. We have a keyword in here saying balance. So that's a keyword we want to circle and highlight. Keywords like balance. That's going to tell us that the angular acceleration is 0. So we have a case where the torque that would twist the system clockwise equals the torque that would twist the system counterclockwise. So the torque that would twist the system clockwise would be the torque caused by this 100 Newton force. And we want to figure out what is the R that we should have it act at. And then the torque caused by this person standing here would be caused by the force they exert perpendicular to the radial line. So that would be the force of gravity, so this person's mass, times little g, times the distance that they are away. So we could find the distance to place that 100 Newton force by taking their 30 Newton mass times g. I'm just going to call that 10. So say g equals 10, which is pretty close to 9.8. So we've got 300 times 1.3 by 100. So that would be 3.9 away. So that's an example problem of just two simple, one torque on one side, one torque on the other side, in equilibrium. So in this problem, we kind of ignored the mass of the board or called it massless. And often we will do that. But I want to tell you how to treat the mass of the board, especially if our pivot isn't at the center of mass of the board. So center of mass is this idea that if we took all the mass in an object and put it at one point, where would that point be? So for a uniform mass board, it would be at the center of the board. For like a bowling ball, it would be at the uniform mass, it would be at the center of the bowling ball. And these were often the points that we drew our free body diagrams from. So if we have a meter stick pivoting off of its center of mass, like the center of mass is here, but we have our pivot here, then we need to treat the mass of the meter stick and the force it exerts associated with it. Has a torque that's happening at the center of mass. So it would be a torque equivalent to the weight of the meter stick, the mass of the meter stick, times little g, multiplied by the distance that the center of mass is from the pivot. So that helps us do a few more complex torque problems. So I'll end it here. This is torque as Fr, and then I'll make another video for torque and angular acceleration.